Hello students, welcome back. Today we are diving into two very important topics, steric inhibition of resonance, also known as SIR, and steric inhibition of protonation, known as SIP. One of my viewers requested me to make a video on these two concepts, and I guessed many of the students would also struggle with this particular topic. So that's the reason I'm making the video. First, we will master the core concept. Then, we solve some practice questions. Finally, I have left a few challenge questions for you at the end of the video. Make sure to solve those final questions. Drop your answers in the comment below and don't forget to subscribe the channel. So, let's get started. First, let's understand what is the meaning of word steric. In organic chemistry, steric refers to the spatial arrangement of atoms and how their physical bulk or size affects chemical reaction or properties of molecules like acidic strength or basic strength. That's right. We are going to use these two concepts to explain the basic strength of the molecules. So first let's understand what is steric inhibition of resonance. Resonance refers to delocalization of the electrons, especially when there is a conjugated system, like for example, benzene molecule. Let's assume we are attaching this benzene by a group NH2. So now we call this as aniline molecule, and nitrogen will have a lone pair of electrons on the nitrogen. Since the lone pair is in conjugation with this benzene ring, it will also get involved in the resonance. You can see that the electrons are moving from atom to bond, bond to atom, nothing but it is resonance. Why this is happening? Because the molecule is being planar. The lone pair is in the same plane as the pi electron cloud which is present on the benzene. That's why the lone pair is involved in the resonance. Let's take one more example. I'm going to take a derivative of the aniline. So since the two methyl groups are on the nitrogen, you can call this as N, and dimethyl aniline. And at second and sixth position also, I'm taking two methyl groups. You can see if I start numbering from the ipso carbon, the groups are at sixth and second position, right? Therefore, you can call this as 2, 6 dimethyl, right? So what will be the name of the molecule? N, N 2, 6 tetramethyl aniline. You can call this way also. Now, the lone pair of electrons present on the nitrogen, will it still undergo resonance in this case? No, that itself is called as steric inhibition of resonance. Earlier, the atoms present at the second and sixth positions were hydrogens. There are two hydrogens here, and hydrogens take small space because of their size, whereas methyl groups are bulkier as compared to the hydrogen atoms. Because of this, they take more space, right? Steric effect is all about the space here. So because all four methyl groups, if they are in the same plane, all of them compete for the space. So we call this as steric hindrance. Because of the steric hindrance, what happens? There is this carbon-nitrogen bond rotation, and this tries to go out of the plane, or it is perpendicular to the plane of the benzene ring. Due to this non-planarity, the lone pair cannot undergo resonance. Can it undergo resonance? No. The resonance is being inhibited. So it is being stopped due to the bulkier groups. Bulkier group causes steric hindrance. So we call this as steric inhibition of resonance. So there is a SIR effect in this molecule. Now, how does it matter? Why do we have to study this? We have to study this to understand the basic strength of the molecules. Suppose the question is, which among these two molecules is more basic? So how do you explain the basic strength of these two molecules? For that, let's make use of the SIR concept. In order to act as a base, they have to donate the lone pair. How easily they donate the lone pair will determine their basic strength. In case of aniline, the lone pair is not available for the incoming proton. Why so? Because it is undergoing resonance. While undergoing resonance, it gets stabilized. But what about in this case? It cannot undergo resonance. That means what? It is easily available for the incoming proton. Hence, N, N dimethyl 2,6 dimethyl aniline or tetramethyl aniline is more basic than the corresponding aniline molecule. Similarly, I have given one more example here. So students, to summarize, SIR refers to how bulky groups twist a functional group out of plane to stop the resonance, like in case of this molecule. It increases basicity by trapping the lone pair on the nitrogen in this molecule. So this is the best example to remember and apply the SIR concept. Now let's understand what is SIP with an example. The SIP effect is mainly known for amine molecules. Why amines are used here? Because they are popular Lewis bases. For example, let's take an amine like RNH2. When it accepts proton as it is a Lewis base and it's going to form ammonium ion like this. So the capacity to accept the proton depends on how stable the conjugate acid is. If this is base, then it is going to form conjugate acid, right? So how stable is this conjugate acid? Better the stability of the conjugate acid, corresponding base will be a stronger base. Let's take two aromatic amines. One is aniline. See, this is always a comparison study. This is where it will help you to find out the basic strength of different molecules. This is aniline, and the next molecule I'm going to take is 2,6 dimethyl aniline, like this. Which among these two molecules is more basic? That is better explained by the protonation concept. When aniline accepts the proton, it's going to form anilinium ion like this, NH3 plus. Same with this molecule also. It's going to accept the proton and this also is going to form anilinium ion. As I told earlier, how stable is a conjugate acid? That is what we need to discuss here. When you have three hydrogens here, you can see, you can elaborate the molecule to understand or imagine this better. You see, all the three hydrogens not feeling any steric hindrance because there are no bulky groups here, isn't it? But look at this nitrogen which is attached to three hydrogens like this. There is some sort of hindrance due to the methyl groups over here. So literally they are fighting for the space. When they do so, this is not so stable. So what happens? It will revert. That means what? It is trying to attain the equilibrium by giving away the proton. If it's giving away the proton and reverting, do we consider this as a good base? No. It is not as good base as compared to the aniline molecule. Hence, aniline is considered more basic than the 2,6 dimethyl aniline molecule. So, to summarize, SIP refers to the bulky substituents, okay, which are nearby. They have to be 2,6 only. If they're at 3, 4, 5, we are not using this concept. Remember this. When the bulky substituents are nearby and they create steric hindrance, that prevents the proton from approaching the molecule easily. And this decreases the basicity by creating steric hindrance. Many students might think that, okay, so there is a resonance here also. Then why we are not considering the SIR? So for that, the note is here. SIP is usually stronger than SIR. That is the reason, although there is a resonance, right? So always there is one phenomena which predominates the other. So in this case, the steric inhibition of protonation, the competition for the space after it accepts the proton is much more as compared to the resonance phenomena. Here, the lone pairs are already used up to donate the proton. So after that, what happens? It's not stable. So it's reverting. That's why SIP is predominating over SIR. That's why we consider the aniline more basic than 2,6 dimethyl aniline. Many students, what they think is that methyl groups are electron donating. That's why they increase the basic strength of this and they lose marks in the exam with this concept. No, that is not correct. So remember, it's because of the SIP reason. We cannot apply this particular concept to the acids because here it is about the protonation. In case of acids, they donate the proton, but they don't accept the proton. That's why SIP is generally not used for carboxylic acid because they donate proton rather than accepting the proton. SIP is mainly for the amines but not carboxylic acids. However, SIR is important for aromatic carboxylic acids, which is better explained by ortho effect. How so? For that, I'm going to take an example and explain this. Let's understand the basic strength of anilines using SIR and SIP effects. I've already given the pKb values for the molecules. The pKb values will tell you the basic strength. Lower the pKb value, the basic strength will be higher, remember. So which of the given molecules have the least value? This one. N, N dimethyl 2,6 dimethyl aniline is having the least value. That means what? D is more basic among the given molecules. And then which molecule will be more basic? Molecule C, that is N, N dimethyl aniline. And then we have aniline molecule, which is A, and the least would be molecule B. So this is based on the pKb values. But you can't remember pKb values for all the molecules in order to solve such questions. In that case, you can use these two concepts. How to do that? In this molecule, you see there are 4 methyl groups. Because of this, there is a steric hindrance. That means what? The nitrogen will go out of plane. The lone pair is not available for the resonance. If it is not available for the resonance, it can donate the lone pair to the incoming proton easily. Hence, that is the most among the given molecules. How did I explain this? Steric inhibition of resonance. So, this is explained by the SIR. Let's see why this molecule is least basic. When the lone pair is given to the proton, it's going to form a conjugate acid, right? And then what happens? It's going to get involved in the competition for the space because now you have one additional hydrogen, isn't it? That's why it will revert. That means what? It is the least basic. And how did we explain this? Steric inhibition of protonation. Then how do you explain for the molecules A and C? You can explain it using inductive effect as well. See, N, N dimethyl means what? They are electron donating groups. So they increase the electron density on nitrogen. That's why it will donate the electrons easily to the incoming proton. Whereas in this case, since they are involved in the resonance, not available for the incoming proton. Hence, it is less basic than C molecule. You can also explain it this way. Molecule D and C are tertiary amines. Tertiary amines are more basic than the primary amines what we have here. That's why you can arrange these two molecules first and then these two molecules. And you can compare between each molecule. So what will be the correct order now? D, C, A, B. Now let's apply the SIR effect to explain the acidic strength of aromatic carboxylic acids. As I told earlier, the SIP cannot be used here because carboxylic acids donate proton. They don't get protonated. That's why this is not applicable. The SIR effect increases the acidic strength of the ortho-substituted benzoic acids, making them stronger acids than the standard benzoic acids or their meta or para isomers. This phenomena is also known as ortho effect. The best evidence for this phenomena is their pKa values. I have given the names of the molecules along with their pKa value. Remember, lower the pKa value, more will be the acidic strength of the molecules. Which molecule is having the least value? Molecule C. Because you can see there are ortho substituents. That means what? There is a bulkiness here. So literally they will kick off this hydrogen as proton. So the formed carboxylate is not undergoing resonance with the benzene ring as it is inhibited due to the ortho substituents. Then which molecule do we have? It is orthomethyl benzoic acid, molecule B. And then the least acidic is benzoic acid, as there are no bulky substituents at the ortho position. So what you understand from this, whenever there are bulky substituents at the ortho position, the acidic strength of the benzoic acid increases. Similarly, when there are bulky groups at the ortho position, for aniline molecule, its basic strength will also increase. And for both of them, the reason is SIR effect. Now let's solve a question based on this in order to understand the concept better. Now time to solve the question. Consider the following four compounds 1, 2, 3, 4. Choose the correct statement or statements from the given options. Before we read out the options, let's analyze the molecules given here. You can see this is trinitro N-N-dimethyl aniline. This is also called as substituted picromide, because this is picromide molecule. Okay, so on nitrogen, you see there are two methyl. Therefore, this can be N-N dimethyl picromide, and this is picromide. And this is N-N dimethyl aniline, and this is simple aniline molecule. Let's read out the first statement. Anilinium salts of compound 1 are largely hydrolyzed in aqueous solution. What does that mean? When this accepts the proton, right? Will it be hydrolyzed in aqueous solution? For that, we need to know, will it form this anilinium ion at all? Yes, it does, because it is a strong base. Why is it a strong base? Although we have 3 nitro groups which withdraw electrons here, still the lone pair will not undergo resonance due to SIR effect. There are bulky groups at the ortho position, the lone pair will not undergo resonance. That's why we call it as steric inhibition of resonance of the lone pair of electrons present on the nitrogen. If it is not undergoing resonance, it will be available for the incoming proton. If it is accepting the proton, that means it is going to form anilinium salt. And will it be hydrolyzed in aqueous solution? Yes, because it will be in ionic form. Ions can be hydrolyzed in aqueous solution. So this is a correct statement. Compound 2 is insoluble in aqueous acids. That means what? Will it donate this lone pair of electron? No, not possible, because we don't have any bulky groups on the nitrogen. And you see there are nitro groups here which are electron withdrawing. So there is no inhibition for the resonance. So it is undergoing resonance means what? It is not available for the incoming proton, not forming a salt. Since it is not in ionic, it will not be soluble in the aqueous medium. So compound 2 is insoluble in aqueous acids. This is also correct statement. Now let's analyze the option C. Compound 3 readily undergo hydrolysis to form picric acid. So this is what? N, N dimethyl aniline. How will it undergo hydrolysis? Hydrolysis means what? The OH minus basically should replace this, and it's supposed to form a picric acid. What is picric acid? This is picric acid, right? So there are no nitro groups on this molecule, so it will not undergo hydrolysis. So this statement is wrong. In fact, you can see that this molecule, maybe if you do the diazotization followed by hydrolysis, then it will form a picric acid. That's the reason it's called as picromide. Now let's see the last statement. Compound 4 is more basic than compound 1. This is also incorrect, because we know that due to SIR effect. So here they're saying aniline is more basic than this. Not correct. So among the given 4 options, only A and B are correct. So this is how you have to apply the concepts what you have learned on such questions. I have given some questions at the end of this video. Please do solve them and comment your answers to know the key answers. And please don't forget to subscribe the channel. Thank you.